Hi everyone, myself Dr. T. Siva Nageswara Rao, working as Assistant Professor of Mathematics in the Department of Mathematics and Management Science. In previous lecture, I explained about verification of Cayley-Hamilton theorem, how to find power of a matrix and inverse of a matrix, simplification of matrix polynomial using Cayley-Hamilton theorem. Now I am going to explain properties of eigenvalues and eigenvectors. The first property is the sum of eigenvalues of capital A is equal to trace of capital A. Now what is trace of A? Capital A is a square matrix anyway. The trace of A is sum of the diagonal elements. So the eigenvalues, what are the eigenvalues you are obtaining from capital A? Its sum should be equal to trace of A. And one more is the product of the eigenvalues should be equal to determinant of the matrix capital A. You need to verify these two conditions. And next, third property, if one of the eigenvalue is 0, then A is a singular matrix and non-invertible matrix. Why? Because the determinant of the matrix is product of the eigenvalues. If any one of the eigenvalues is 0, obviously product of the eigenvalues is equal to 0. It shows determinant is 0. If determinant is 0, the inverse of the matrix does not exist. So that is the reason A is singular. And one more property, if lambda is an eigenvalue of capital A, then the k times of lambda is the eigenvalue of A power k. Assume that I given one matrix capital A, its eigenvalues are 1, 2, 3. Then what are the eigenvalues of A power 4? The eigenvalues of A power 4 are 1 power 4, 2 power 4, 3 power 4. This is what I given as next property. If lambda 1, lambda 2, lambda 3 and so on, lambda n are the eigenvalues of capital A, then lambda 1 power k, comma lambda 2 power k, comma lambda 3 power k are comma so on, lambda n power k are the eigenvalues of A power k. Next property, if lambda is eigenvalue of capital A, then 1 by lambda is an eigenvalue of A inverse, provided A is invertible. A is invertible means determinant of A does not exist, A inverse is possible. If determinant of A is not equal to 0, means none of the eigenvalue is 0. Why? Det A not equal to 0 means product of the eigenvalues is equal to determinant. Det A not equal to 0 means none of the eigenvalue is 0. So we can able to talk about its reciprocal. Hence, we will talk about its reciprocal as 1 by lambda. So if lambda is an eigenvalue of capital A, then its reciprocal is the eigenvalue of A inverse, provided A inverse is exists. Now this is next property. For an upper triangular matrix, the eigenvalues are diagonal entities. Similarly, for lower triangular matrix, the diagonal elements as eigenvalues. Similarly, for diagonal matrix also, the eigenvalues are its diagonal elements. So for upper triangular matrix, lower triangular matrix and diagonal matrix, the eigenvalues are just its diagonal elements. Now next property, if capital B is equal to P inverse into A into P, then A and B have same eigenvalues. See, in view of diagonalization, if you are observing this formula, in place of B we have capital D. Now what is capital D? Capital D is a diagonal matrix in which the diagonal elements has eigenvalues of capital A. So if you are replacing D with capital B, then the eigenvalues of capital A and capital B are same. Here the condition is capital P is non-singular matrix. Det P not equal to 0. Then only P inverse will exist. Next property, if lambda is an eigenvalue of non-singular matrix capital A, then what is the eigenvalue of adjoint A? The eigenvalue of adjoint A is det A divided by lambda. Now next properties. Previously, maybe in matrices and calculus, first unit types of matrices like symmetric, skew symmetric, orthogonal matrix, etc. etc. Now we will discuss some of the properties of eigenvalues. What are the eigenvalues of symmetric matrix, eigenvalues of skew symmetric matrix, eigenvalues of orthogonal matrix. The eigenvalues of real symmetric matrix are always real. A transpose is equal to minus A. What is A transpose is equal to minus A? A square matrix capital A is said to be skew symmetric if A transpose is equal to minus A. So it represents skew symmetric. The eigenvalues of skew symmetric are either 0 or are purely imaginary. What are the eigenvalues of symmetric matrix? Are all real. Coming to skew symmetric matrix, either 0 or are purely imaginary. Now orthogonal matrix. What is orthogonal matrix? A into A transpose is equal to I. Similarly, A transpose into A is equal to I. You need to check both the conditions. What are the possible eigenvalues of orthogonal matrix? The eigenvalues of orthogonal matrix whose absolute value is always equal to 1. That is what modulus of lambda is equal to 1. So these are the properties of eigenvalues of different matrices like symmetric matrix, skew symmetric matrix, orthogonal matrix. Now we will discuss about properties of eigenvectors. If capital X is an eigenvector, then Cx is also an eigenvector corresponding to same eigenvalue. It means if capital X is an eigenvector corresponding to the eigenvalue lambda of the given matrix capital A, then C into capital X is also an eigenvector corresponding to capital A. The eigenvectors corresponding to distinct eigenvalues are always linearly independent. In view of previous lectures, we discussed about eigenvectors corresponding to distinct eigenvalues. Take such eigenvectors corresponding to distinct eigenvalues, form a matrix. The columns of the resultant matrix are eigenvectors corresponding to distinct eigenvalue. Find its determinant. Find the determinant of that matrix. Definitely you will get not equal to 0. If it is equal to 0, then we will say the eigenvectors are dependent. Now what is this property? If eigenvalues are distinct, the corresponding eigenvectors are linearly independent. Obviously the determinant of such matrix which contains columns as eigenvectors of the distinct eigenvalues not equal to 0. Then it shows eigenvectors are independent. For a real symmetric matrix, the eigenvectors corresponding to distinct eigenvalues are orthogonal. Assume that I given 3 by 3 matrix which is symmetric, that is A transpose is equal to A. We will find eigenvalues. Assume the eigenvalues are distinct. Anyway, we will find the corresponding eigenvectors. The corresponding eigenvectors are always perpendicular to each other. How to identify the vectors are perpendicular to each other? The dot product between two vectors. Like that, we will do all possible dot products between three vectors. The dot product obviously equal to 0 vector. Hence, dot product is equal to 0, not 0 vector. Then we can say the eigenvectors are perpendicular to each other. If eigenvalues are not distinct, then obviously the eigenvectors are not perpendicular to each other. Next one. A matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Previously, we done diagonalization like P inverse into A into P is equal to D. Without applying this formula, if you want to say whether the given matrix is diagonalizable or not, it is enough to verify the corresponding eigenvectors. The eigenvectors corresponding to eigenvalues are linearly independent or not. If it is linearly independent, then we can say the matrix is diagonalizable. And one more important property is this one, geometric multiplicity, algebraic multiplicity. Geometric multiplicity, algebraic multiplicity. What is algebraic multiplicity? Algebraic multiplicity is the number of times eigenvalue is repeated is called geometric multiplicity. For suppose I given matrix capital A, the eigenvalues are 1, 2, 3. What is algebraic multiplicity of 1? 1 only. Why? The eigenvalue 1 repeated only one time. What is the algebraic multiplicity of 2? 1 again. Why? Because it is repeated only once. What is algebraic multiplicity of 3? Only 1. One time it is repeated. Assume that I given matrix capital A whose eigenvalues are 1, 1, 2. Now what is algebraic multiplicity of 1? 2. Why? Because it is repeated twice. What is algebraic multiplicity of 2? 1. Why? Because it is repeated only one time. Now this is what algebraic multiplicity. The number of times the eigenvalue is repeated. Now coming to geometric multiplicity, the number of linearly independent eigenvectors corresponding to given eigenvalue is called geometric multiplicity. And one more thing you need to remember, there is a relation between geometric multiplicity and algebraic multiplicity. The geometric multiplicity never exceeds algebraic multiplicity. So the geometric multiplicity is always less than or equal to algebraic multiplicity. So this is about the properties of eigenvalues and eigenvectors. Hence, in this unit, till now, we learn about how to construct characteristic matrix, how to find its determinant, how to find characteristic equation, how to find roots of the characteristic equation, those are all called eigenvalues, how to find eigenvectors, how to diagonalize the given matrix capital A, how to verify Cayley-Hamilton theorem, how to find power of a matrix, inverse of a matrix, matrix polynomial simplification by using Cayley-Hamilton theorem, and what are the different properties of eigenvalues and eigenvectors. Thank you one and all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.